In this video, we're going to take a look at section 6.1. So we're going to start chapter 6, which is circles. We've already looked at some circle terminology from chapter 1, and I just want to go ahead and review that right now. So we're going to use this figure here to review some circle vocabulary. So a radius, remember, goes from a segment from the center of the circle to a point on the circle. So segment OE is a radius, segment OA, and all radii are congruent. A chord goes from one point on the circle to another. It could pass through the center, that would be a diameter, or it doesn't have to. So DC is a true chord that's not a diameter, whereas AB is a chord that is also a diameter. And then that means segment AB is a diameter. A tangent is a line that intersects a circle in one point. So line TG is a tangent, and T is the point of tangency. A central angle is an angle whose vertex is the center of the circle. So for example, angle EOB is a central angle. So is EOA, that is also a central angle. A minor arc is less than a semicircle. A semicircle is an arc whose endpoints are the diameter of the circle itself. So for example, arc ATB is a semicircle. So is arc ADB, or you could call that BDA. So a minor arc is less than that. So for example, arc AT is a minor arc. Arc DC is a minor arc. A major arc means it's going to be more than a semicircle. So you want to make sure you go through that diameter. So like arc DAB, for example. Or I think I did DAC there. That is a major arc. There are lots of major arcs in this particular circle. You could do AEC, DCT. So a couple other vocabulary words that we want to review. So tangent segments are actually just very similar to tangent lines, except for there are segments and one endpoint of the segment intersects the circle. So when we think of a tangent segment, for example, let's go back to here. Here's circle O. We would say segment TG is a tangent segment. So end point that touches the circle, that's the tangent segment. An intercepted arc, this has to do with angles, okay, or chords. So the intercepted arc is the arc whose endpoints are the endpoints of a chord or whose endpoints lie on the sides of an angle. Okay, so let's say we have circle O. My circle drawing is not super great today. So let's say we had this central angle, okay? And these points here are on the sides of the angle, they're on the ray. And this arc here has the endpoints of that angle, of those points on the angle. So this is an intercepted arc. Similarly, let's say we have a chord here. So these points are the endpoints of the chord and the endpoints of this arc. So this is an intercepted arc. that's going to be really important in part of our investigations. And then tangent circles are just two circles who touch once, intersect at one point. So circles who intersect at one point. So circles can be internally tangent, which means these circles are internally tangent. They touch at this point, but one is inside the other. Or externally tangent. These circles are externally tangent. I also want us to remind ourselves, and we did this in chapter 1 too, but the measure of the arc is the measure of its central angle. And that the whole circle always adds up to 360. Okay, so we want to find the measure of arc PQR. So here's PQR. Okay, so a couple things we want to know. This arc here, arc QR, notice how it's intercepted by this angle, and this angle has a measure of 48 degrees. So arc QR has a measure of 48 degrees. Also, this segment QP is diameter because it passes through the center. So this arc has a measure of 180 degrees. So if we want to find the measure of arc PQR, we add the 180 to the 48, so that means it's 228. All right, so for the first investigation, I just want us to remind us of that. So for the first investigation, you're going to need a compass and a straight edge. And on the next page, we're going to draw a large circle, label the center O. And remember, the center of the circle would be where your stylus is, so you can go ahead and mark off where your center is going to be, set your stylus there, and then go ahead and use your compass and draw a circle. So I'm not using a compass, and my circle is not that great. Your circle will be amazing. So we have our center, okay. And we're going to use a straight edge, and we're going to draw a line that appears to touch the circle at only one point. We're going to label that OT, and then we're going to head and construct segment OT, and then we are going to look at the radius. Okay, so for example, let's pick this point here. We're going to label it T. Go ahead, take your ruler and line it up so it looks like it's only going to touch the circle at this one point here. Okay, oh, we're making a segment. Let's go look at the picture. No, we're making a line. Okay, perfect. This is point T. And again, you want to just really make sure this is using your straight edge and make sure it looks tangent. So then go ahead and use your straight edge and connect points O and T. So OT is a radius, right? It goes from the center to a point on the circle, and then this line that has T on it is a tangent line. So what I want you to do is go ahead and measure this angle created here. Okay, what can you use your protractor to measure the angles at T? So go ahead and line up your protractor and measure this angle and measure this angle. You should see, hopefully, that they are 90 degrees. So that means the tangent to a circle is perpendicular at the point of tangency, to the radius drawn to the point of tangency, excuse me. All right, so I have an example that we're going to take a look at here. We know that line AT is tangent to circle P, whose center is the origin, and we're going to find the equation. So this is a good coordinate geometry review question. So using what we just learned, if I draw my radius, segment AP, it is perpendicular. And what do I know about segments or lines that are perpendicular? So perpendicular have opposite reciprocal slopes. So that means if I'm going to find the equation of line AT, I first need to find its slope. To do that, I'm going to find the slope of AP and then use the opposite reciprocal. So slope is change in y over change in x. One of my points is the origin, the other is 3, 9. So 9 minus 0 over 3 minus 0 is 9/3 or 3. So that means the slope of line AT is going to be negative 1/3, right? This is 3 over 1. Reciprocal is 1/3. So to find this line, I'm going to use point slope form. And the point, of course, I'm going to use is point A. So y minus 9 equals negative 1/3. That's my m. So it's y minus y1 equals m times x minus x1, which is 3. So this would be negative 1/3 x, and then plus negative 1/3 times negative 3 is positive 1, and then I'm going to add 9 to both sides. So y equals negative 1/3 x plus 10. And that's the equation of my line. All right, for this next investigation, we're going to learn something about the lengths of segments tangent to a circle from a point outside the circle. So again, pick a point for the center, label it E. Go ahead and open up your compass, put your stylus on E, and draw your circle. So we're going to choose a point outside the circle. Any point will do. Okay, we'll do one over here and call it N. And we're going to draw 2 lines through N tangent to the circle. And you can kind of see the picture. So here's our N, and there we're going to draw 2 lines tangent to the circle. So you want to use your straight edge, kind of line it up so that from point N, you're going tangent this way, and then tangent this way. Again, yours will look a lot nicer than mine because you're using a compass and a straight edge. So now, okay, we want to draw 2 lines through point N tangent to the circle. Mark those lines A and G. So here's G and here's A. Mark those points, excuse me. Use your compass to compare segments NA and segment NG. Segments such as these are called tangent segments. So if you go ahead and put your stylus on N and compare the length to point A and the point G, you should find out that they are the same length. And so tangent segments to a circle from a point outside the circle are congruent. And then the question is, right, is what shape is formed that could help us prove this conjecture? So this picture here will help you, okay? But we could also go back to our own. So if we know this segment is congruent to this segment, here's points A and G, our points of tangency, and we have radius AE and radius EG, we know that radii are also congruent. So guess what shape we have here? We have a kite. And so a kite can actually help us prove this using one of our triangle congruence shortcuts. All right, we're going to take a look at some examples. Rays R and S are tangents. What is the measure of W? Okay, so we're going to use some of the conjectures we just learned. This angle here is 54 degrees. These angles here are 90 degrees. Again, how do I know that? Because these are radii and this is a tangent segment. This shape formed is a kite. We just talked about that. And a kite is a quadrilateral, and of course it has to sum to 360. So if I do 90 plus 54, or 180 plus 54, and then I go ahead and subtract that from 360, that is going to give me the measure of this angle here, which is 126 degrees. The second example is very similar to the first one. Turns out we have a quadrilateral here, and these two angles have to be 90 because of radii being tangent. And then when you use add up the measures you have and then subtract from 360, you get 105. This next one